Okay, now let's prove the proposition 1.3, basically the arc length formula. If gamma from A, B to C is piecewise smooth, then gamma is of bounded variation, and the total variation is equal to the integral from A to B absolute value of gamma prime of t dt. Okay, so remember in the last video I already mentioned that gamma take the image in the images in the complex number, so the gamma of t will have x of t plus iy of t. So gamma prime of t is going to be x prime of t plus I y prime of t, and the modulus of gamma prime of t is, you get the square root of x prime of t squared plus y prime of t squared. So this is exactly the arc length formula, and the total variation is the length of the image gamma. Okay, so that's the connection between the complex analysis and and calculus. Okay, well, let's see the proof. Here it is, the gamma is piecewise smooth, and you basically what we do is that we only show the region the result for the gamma smooth. If it's piecewise, you just apply this for each of the smooth region. Okay, so assume that gamma is smooth. Smooth means differentiable, and the derivative is also continuous. That is smooth, right? Then let's see. So here, gamma is differentiable, and gamma prime is continuous. So that's what we mean smooth. Okay, now let's see how we get this. What is the total variation? Total variation is a supremum. Remember, total variation is a supremum of variation of gamma and p, or the supremum. P is a partition. Okay. Okay, so it is related to the partition. So let P be A equal to T0 less than T1 less than T2 less than Tm equal to B. Okay, then then what? What is this variation? Variation of a gamma with respect to P. By the definition, it is sigma gamma of tk minus gamma of tk minus 1. K is from 1 to m. Right? And now let's check. We have differentiable function. Differentiable function, we know we have the mean value theorem, MVT. MVT can be used to here is another MVT. No, this place is not MVT. Later, we use a fundamental theorem, FTC, fundamental theorem calculus. We will use MVT later. Fundamental theorem of calculus. Fundamental theorem of calculus says the gamma of tk minus a gamma of tk minus 1 is the integral from tk minus 1 to tk gamma prime of t dt before the modulus. Okay, so this is before the modulus. And then we know that the integration has a this is a real integration. Remember, this is a real integration because the variable is a real variable. And for the real integration, if you move this ops value into the integral, you get the inequality. So this is integral from tk minus 1 to tk, ops value of gamma prime of t dt, right? And then you get the additivity of the integral. This is integral from a to b gamma prime of t ops value dt. Okay, so for whatever partition, the variation of gamma with respect to p is always less than or equal to this constant number. So this is a upper bound. Supremum is a least upper bound. Hence, we get the total total variation, the least upper bound. Total variation should be less than or equal to this integral. And because it has an upper bound, so this gamma is of bounded variation, right? This proposition actually has two parts. Part 1, we need to show this gamma is of bounded variation. Part 2, we have this total variation formula, two parts. So here we finish one part, and we get a partial relation. And next, we're going to show this the other direction. It should be greater than or equal to the total variation. The total variation will be greater than or equal to this number. Okay, so what is the other one? So remember that we assume this gamma prime is continuous. Gamma prime is continuous over the interval AB. AB is a closed interval, so gamma prime is uniformly continuous. Okay, uniformly continuous. Uniform continuity means given epsilon greater than 0, there is a delta 1. Let's put delta 1. We will have several deltas. So this first delta, delta 1, such that for s minus t ops value less than delta 1, we have gamma prime of s minus gamma prime of t modulus less than epsilon. So this is our uniform continuity. Okay, so the other one, remember the integral. Here there's an integral AB gamma prime of t modulus dt. This integral is a Riemann integral. Riemann integral means if this exists, means for whatever for any epsilon there is a delta 2 greater than 0, such that if a partition we get a partition P is equal to A is T0 less than T1 less than T2 less than Tm equal to B, with the norm of the partition. Remember, what is the norm of the partition? Norm of partition means that the longest length of the subintervals. right? Tk minus Tk minus 1 is the length of subintervals. You pick up the longest one, and that length is called the norm of the partition. All right? If this norm, such that with a normal partition less than delta 2, if it's sufficiently small, every subinterval is small enough, we have this number integral from a to b ups value of gamma prime of t dt minus Riemann sum sigma k from 1 to m ups value of gamma prime tau k times tk minus 1, the integral minus Riemann sum ups value is less than epsilon. Okay, this is the definition of a Riemann integral, where t or tk are known. What is a tau? Where tau is any arbitrary point, or is any point in the closed interval tk minus 1 and tk. Okay, tk in the small interval. Okay, so let's check this integral. This inequality, if you remove the inequality, remember x less than epsilon, it is equivalent to x is between negative epsilon and positive epsilon. So if we just consider this one, the integral from a to b ups value of gamma prime of t ups value of gamma prime of t dt, the minus it is less than epsilon, so it's going to be less than this Riemann sum and plus epsilon. Just move this term to the right side. Riemann sum plus epsilon. Okay. Tk minus 1 is positive and it's real. For this real number, we can move it into the ups value. So it's like this. And also tk minus 1 is equal to the integral from tk minus 1 to tk dt, right? The difference is always the integral of a constant number 1. So and this is a gamma prime of tau k. It's a constant, so we can move this constant into the integral. Okay, so even though it looks like we're integrating someone, actually we just integrate the constant number. All right. Okay, so we integrate to constant number, and this moment we're going to do some standard trick. I'm going to subtract. This is constant, but gamma prime of a t is not constant. Once we put a t, it's not constant. We subtract it. We add it. Then by the triangle inequality, it's less than or equal to. Okay, and this works for all the partitions with the condition less than delta 2, because once a partition has a modulus norm less than delta 2, this inequality holds. All right. Okay, so for this term here, for this one, we can move this ops value into the parentheses. So it's less than or equal to sigma k from 1 to m integral tk minus 1 tk ops value of a gamma prime of tau k minus gamma prime of a t dt and plus this. And you see here, this is the integral of gamma prime of t by the fundamental theorem of calculus, FTC here. It is gamma of tk minus gamma of tk minus 1 and plus epsilon. Okay? So this one is a variation of gamma with respect to p. And plus this term. We're going to estimate this term. Here, tau k is in the interval, t is in the interval, so the tau k minus t is going to be less than the norm of the p, because of it is actually less than this distance, but this distance is controlled by the norm. It's less than or equal to the norm of the p. So if we assume the norm of p is less than the minimum of delta 1 and delta 2. Delta 1, delta 2, they are independent. Delta 1 is related to the uniform continuity. Delta 2 is related to the integrability of the gamma prime, modulus of gamma prime. So they are independent. So you can find delta 1, delta 2 separately, and then you assume this norm of p additionally less than the minimum number among those delta 2 and delta 1. When it is less than delta 2, this whole process works. When it is less than delta 1, so tau k minus t will be less than delta 1. Then tau k minus t will be less than delta 1. When tau k minus t less than delta 1, remember why we use delta 1? We have uniform continuity, so we get ops value of gamma prime of tau k minus gamma prime of t is going to be less than epsilon. Less than epsilon. So this term is less than epsilon. And be careful here, all the numbers of inside the ops value is a complex value, but with the modulus is a real number. So we can really have inequality. So this is less than epsilon for whatever tau k and t. So let's continue this. It's less than or equal to epsilon plus variation of gamma with respect to p and plus sigma k from 1 to m integral tk minus 1 to tk. And this is replaced by epsilon. You integrate epsilon from tk to tk minus 1. So this is epsilon times tk minus 1 without any other formula. And then you add them. So it's a variation of gamma with respect to p and plus epsilon times b minus a. B minus a. When you add them, you're going to have this telescoping series. And with addition, you will get b minus a. Okay, and this is actually epsilon times 1 plus b minus a, and plus variation of gamma with respect to p. Okay, so epsilon is arbitrary. Let epsilon approaching 0. This is a fixed number. Where? This one, yeah, here. This is a fixed number. It does not depend on epsilon. And this one is fixed number. It does not depend on epsilon. Only this part. So when epsilon approaches 0, this term will vanish. We have the integral from a to b, ops value of gamma prime of t dt will be less than or equal to the variation of a gamma with respect to p. Okay, so we get the other direction. right? And here. No, it's not right. There's one more step we need to focus. Yeah. So when epsilon approaches 0, this partition will change. Yes, this is not correct. I lost one step. When epsilon approaches 0, the left-hand side is okay, but the right-hand side, this changes. This also changes since P depends on epsilon. P depends on this delta 1, delta 2, delta 1, delta 2 depend on epsilon. But this one, the variation, remember the variation is always less than the total variation. So we get, I forgot one step, so I think I got wrong answer at this moment. Okay, so we need to pass it from the variation of gamma with respect to P to the total variation, because this total variation does not depend on epsilon. And this moment, we can recycle this sentence. So let epsilon approach 0 plus, we have integral from a to b of value of gamma prime of t dt is less than or equal to the total variation of gamma. Yeah, this is not correct. It's my mistake. Okay? So even though this part, you don't see epsilon, but actually this p depends on the epsilon. But this variation of gamma does not depend on epsilon. So then you can pass it to the limit. Okay, so you get the integral less than the variation, and the first part, you show the variation is less than the integral. So they equal to each other. And then we finish the proof, right? Okay, so this is one very special case when you have a piecewise smooth gamma, and then it is of bounded variation, and the total variation is equal to the arc length. All right, and we will continue this the lecture in the next video. Thank you.